Professor Genzel. I will introduce shortly, just
Please,
short
please
biographical sketch.
go,
Okay, thank
go.
you. So, dear colleagues, dear friends, I'm happy to introduce our today's speaker, Professor Dr. Reinhard Genzel. A few words about his biography. So, Reinhard Genzel was born in 1952 in Bad Homburg, Germany, and he is one of directors of Max Planck Institute for Extraterrestrial Physics. He is professor also in the Graduate School of University of California, Berkeley, and an honorary professor at the Ludwig Maximilian University in Munich. He is a scientific member of the Max Planck Society and member of United States National Academy of Sciences. His research interests include astrophysics of galactic nuclei, star formation, kinematics and cosmic evolution of galaxies, massive black holes, and experimental infrared, submillimeter, and millimeter astronomy. Professor Genzel has received numerous honors, distinctions, and awards, including Shaw Prize for the Shaw Prize Foundation and the Crawford Prize in Astronomy. In 2020, he received the Nobel Prize in Physics jointly with Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. And today's talk is devoted to the main subject of his research, galaxies and black holes. Please, Professor Genzel, the floor is yours.
Thank you, Andre. Yeah, I mean this topic I'm talking about, it turns out to be one of the current really hot items in astronomy, but also in physics. As you will see, the kind of work we can do experimentally on by analyzing various properties of distant objects we think to be black holes, we can really honestly begin to test the theory of general relativity in the regime which never had been tested before, namely high masses and very close to the event horizon. And as you will see, this interest is closely coupled with the evolution of galaxies because these black holes sit in the centers of galaxies. So, from a cosmic evolution point of view, if we study the evolution of black holes, then we also study the evolution of galaxies. So, you will see how that comes together. Now, of course, the theory of general relativity is now 109 years old. You might think, well, why do we still worry about that? But we do because, as I mentioned, we want to really make sure that as you come close to the event horizon, that the physics is as predicted by the theory. And of course, we have a whole group of towers of physics who've thought about this over the last 100 years theoretically, culminating in the work of Roy Kerr, for instance, and Roger Penrose, Stephen Hawking, and so forth, on basically the recognition that as soon as space-time has more than a critical curvature, then basically you have an object you must call black holes because information, including photons, cannot get out anymore. So the question then in the 1960s was whether such objects might or might not be present in our universe. And that is challenging because, as you will see, most of these things we call black holes are very far away. At the same time, even for very massive objects like millions to trillions of solar masses, the size of the event horizon is extremely small. So initially, the technologies which astronomers had in the optical and then also in the radio were not good enough, and so you will see how that has developed. Now, in a way, most most astronomers would say the first time there was an indication that these objects called black holes really do exist were the so-called quasars. This one here is the first such object in the optical. The quasars were discovered in the radio in Cambridge, England, for instance, and optical pictures like this one here shows obviously a star-like object. It's very faint. You see a little smudge there on the left side. That turns out to be relativistic gas, ionized plasma, which is moving almost at the speed of light. And so that's what people learn. There are these small objects, weak in the optical but very strong in the radio. Then Martin Schmidt, who is the person in the bottom left there, took the Palomar telescope and took a spectrum of this object. And what he found was spectral lines, emission lines, whose wavelength ratios were exactly what you would find in the local universe, but hydrogen, helium, and so forth, but all redshifted in this object by 16%. So how is that possible? Well, okay, the discussion started. If you look at the literature of the next 10 years, it was a hefty discussion of the theoretical community. And then what became sort of the leading explanation is paradoxically the explanation through accreting black holes, as you see in this little sketch down there. So the idea is if you have a massive black hole, well, it will attract through gravity material to come in, also stars. Material presumably will have some amount of angular momentum, so you get a disky-like situation. And inside of this disk, there is magnetic fields, for instance, which create friction in this plasma, so that angular momentum can be removed and material can stream inwards until, of course, you reach the event horizon, at which point, the accreting material disappears for us observers at a distance. But before it disappears, it can convert up to 10 to 40% of the rest mass energy in terms of photons. And so that is 1,000 times more efficient generation of energy in light than even in fission and fusion. And so the idea was, or the proposal was, these quasars are distant objects, very massive, which have a massive black hole that is accreting material. Now, of course, you can make all kinds of proposals. You have to prove it if you're a physicist. And the problem is that these quasars indeed are so far away. This one here is 2.4 billion light years away. If the redshift, which has been seen, is due to the expansion of the universe. So 2.4 billion light years was at the time a sensation because the universe that was known was much, much smaller. So, however, if that object is that far away, then of course what looks like a meager star is in reality a very powerful radiator. It turns out this particular object, 3C273, produces about 1,000 times more energy in a volume of less than a light year than the entire Milky Way. So how you really, how is that possible? Well, the black hole idea might be a good ansatz, but the problem is how would you prove that? And of course, gravity you cannot see through photons or anything like this, but you can sense it as Newton and Galileo and everyone else had done in the solar system through the motions of other particles, objects in the vicinity. So then Donald Lindenbell and Martin Rees, the two people down there on the right side, proposed that if such a distant quasar was an accreting massive black hole, well, maybe there are other massive black holes in other galaxies and closer to us, just not as much accreting, so not very bright. And so if you take that argument and push it to the extreme limits, you could say, well, maybe our own Milky Way has such a black hole. Well, we definitely know that in the Milky Way there is not much activity which you might assign to a black hole, but there are test particles you might use to look for the mass, and that would then be the experiment. So by the end of the 1970s, experiments started around Charlie Towns, Nobel laureate for the invention of the maser and the laser in Berkeley, to look at gas clouds in the vicinity of the galactic center. And that was sort of the start of the hunt in the galactic center, which I have then taken over from Charlie and pushed it to its extreme limits. Also, Andrea Ghez and her team at UCLA did the same. So two independent groups actually went ahead and started to measure initially gas, but then stars. Stars are more reliable, of course, as traces of gravity, whilst gas you can push around in other ways. So it took us 40 years to push from a sort of a first indications that there might be something like a million solar mass object in the center of the galaxy to the current situation where we are really doing high quality experiments which elementary experimental physicists would accept as a good proof. Now, so this is the one way to do this. Another way to look for black holes is through gravitational waves. Turns out that also that story has the same kind of a history as I told you about the galactic center star motions, because it took the gravitational wave community about the same time, 40, 50 years, from the initial tries like the Weber bar and other things, to LIGO and the other experiments, which nowadays allow us to look at, for instance, in-spiraling double black holes. And you see that picture there. That's the first in spiral, which was seen in 2016, and really shows that, initially you have two objects obviously moving around each other, sending out gravitational waves, and then the frequency of the waves increases as the objects come closer to each other, lose energy through gravitational waves, and then in the end, beep, it ends at when the two event horizons, merge. So this evidence we have now for a number of stellar-like objects, 10 to 50 solar masses, and the objects like the galactic center could also be observed, but not from the ground. That is a story probably of the next 50 or so years. Another technique we are now using is very high resolution long baseline radio interferometry, VLBI. That is actually where I did my PhD in Bonn with that technique, and that has now been pushed to the entire globe at very short wavelength and getting extremely high angular resolution in that way. And in 2022, the Event Horizon Telescope collaboration published their first results on the galactic center, but also a little earlier on a nearby massive galaxy M87. And in both cases, there is then, as you will see, strong evidence for a massive object. So we have several techniques available and which are being used nowadays to look for these objects. Now, let's go a little bit into the technology here. Of course, if you want to resolve the size of a distant object, well, you have a telescope which has a diffraction limit, which is possibly as small as the event horizon. Now, that is actually not easy because number one, you need to have a really big telescope in order to match it to the, micro arc second sizes of massive black holes. The other problem is the Earth atmosphere, because the waves pass into the Earth atmosphere and are then perturbed by the turbulence of the Earth atmosphere, so that the image which is then formed at the telescope is far away, far worse than diffraction limit. That can be overcome with a technique called adaptive optics, where you basically measure the incoming wave, and then you have a quantum an optical feedback system to then restore the diffraction limited resolution. I'll say a little bit more in a second. So that's essentially the way one works. And broadly speaking, the technology, the techniques we are using here, or in fact the radio astronomers or the gravitational wave people, is interferometry, Michelson interferometry. So you will recall that Albert Michelson was the first one who tried out to use interference of light and resolve stars. He did that on a 180-inch telescope in California. There you see it. And he mounted a bar on top of it with reflectors, which would reflect the lights from a distant star into the telescope and then form an image. Now, if this works, then you get what we call fringes, and you see that on the right side. And this separation of the fringes is, a measure, or the size of the fringes is a measure of the resolution. So the wider you make larger you make this retroreflector, then the sharper the fringes become, the higher the resolution becomes. And all the other techniques in the optical and radio are working very much the same way. So the Event Horizon Telescope uses the entire Earth and short radio waves to try exactly that. The gravitation wave people use the same technology to interfere the gravitational wave signal and get fringes. And we do the same thing now with optical telescopes. What you see here is the currently top telescope we have in the world of four 8-meter telescopes in the Atacama Desert in Chile. Very, very great place because of the dryness of the atmosphere, very, very clear nights. And so we combine the light interferometrically of all the four telescopes and then bring that together and use adaptive optics to make them diffraction limited. And then in the end, we have the resolution of an equivalent 150-meter telescope. Okay, so it's very much the same technique. It's interesting that, Michelson knew it all, and but it took a long time to get the techniques down to the quality we have now. Now, you might think that this is sort of a dream and a nice propaganda video, but the reality is like that. So we started initially in astronomy with single laser beams in the sodium D line, and basically in that way we would create a reflection, or a scattering of the laser in the upper atmosphere, generate a laser star, as we say, which then runs back through the atmosphere and can be made very bright. And that we use with deformable mirrors to basically correct for the distortions of the Earth atmosphere. So you can do this with single telescopes, and that's now been done for about 15, 20 years. But since, in fact, last week, we can do it for all four telescopes in Chile, and that's been a very great triumph. So we can combine the technology of interferometry and laser guide star correction of the imagery. The sensitivity we now have, compared to the first attempts by Charlie Towns and also Michelson, is about 1 million times better in sensitivity than what they had. So optical near-infrared wavelength interferometry is really the way to go to very compact objects. So here is a picture of the center of our Milky Way in the near infrared. You cannot do this in the optical because between us and the galactic center, although it's only 27,000 light years, so far less than other galaxies, there's a lot of dust in the line of sight, and that dust is basically absorbing the short wavelength radiation. So we have to go to longer wavelength, either radio waves or, in this case, near infrared waves. And then we use the technique of adaptive optics to make the images sharp. So in this case, what you have is a single 8-meter telescope, then using a laser guide star to make a very sharp image of the central few light years of our Milky Way. And what you see there is a tremendous concentration of stars, of very bright but also faint stars, of course. And the radio astronomers also find there this greenish object, which is a very compact radio source. So there's obviously our laboratory. If this radio source is a black hole, what we want to do is we want to measure the motions of the stars and see whether, well, Kepler's laws are fulfilled, or even better, of course, general relativity, and whether there is a compact object. Fast forward, 25 years, and we are in the current epoch where indeed we can do this now at exquisite resolution with the interferometers, and we measure individual stars, not only their motions, but actually their orbits. So you see this here, that there are obviously stars in the very center close to the red cross, which is the radio source, on scales of the solar system. And the motions, when the stars come close to the radio source, Sagittarius A star there, are several up to 8,000 kilometers per second. So clearly there is obviously something massive there. And by using these stars at different distances, we can measure the mass distribution in the galactic center. Indeed, what we can do nowadays with the interferometry is we can see the motion of the stars in a given year. It's remarkable to see that, in this particular case, there is a star which comes close to Sagittarius A star on the distance of Neptune. So it's a very, very compact source, only about 15 light hours. And that, of course, is the exact way we would like to test the postulate that there might be a black hole. Now, we have to do this across an entire orbit, which for this particular star here, S2, takes 16 years. But you see, it's a very elliptical orbit. and Sagittarius A star is this dot, this black dot there on the bottom left. And these are measurements of both the Keck group and our group. And so the data are in very, very good agreement that this object, which we call S2, is on an elliptical orbit which approaches the radius of Sagittarius A star to about 15 light hours once every 16 years. So during the last peri in 2018, you see that at the bottom here, we could see the motions of the star, and not only from month to month or year to year. Now we could see it from day to day. Okay, and that's because of the 7,000 kilometers per second. We can also measure spectra and thereby get almost all the information you need to, understand fully the gravitational potential. So you have measurements of X and Y on the sky. You have a measurement of the velocities in X and Y and in Z through the spectrum, Doppler effect. The only thing you're missing is the line of sight position. And that you gain by getting whole orbits and solve then for the best fitting orbit. Okay. So in the end, we can actually get 6 out of the 6 necessary variables to infer a mass at that peri distance, and you do it for another star and another star until you know something about the mass distribution. Now, I said already that one of the other goals here, other than proving that there is a central a compact object of great mass, is to test general relativity. So the first post-Newtonian effect, which you might expect to see, is the gravitational redshift. So if you have a star with emission lines or absorption lines coming close to the black hole or the compact source, then the waves, of course, coming at us have to move out of the gravitational potential and get redshifted. You see this below in a diagram where we've subtracted the Newtonian orbit, and so you see the velocity shift, the residual velocity shift, where Newton would see no change, whilst general relativity predicts that red curve. So at the closest point, a 200 kilometer per second red shift, and indeed we see that. And so in that sense, we can test general relativity in this so far untested regime. The next thing, however, is you want to get yet closer. These stars, which I show you here, typically orbit at distances from the black hole of, 1,000 to several thousand times the event horizon. Now, there could be other configurations of mass which are compact. Like, for instance, you could imagine a cluster of stellar black holes or a cluster of neutron stars or something like this. So what you really want, in addition to these tests, is to come as close as possible to a few times the event horizon. And that we can do now too, with two techniques. One is with our interferometry in near infrared. Sometimes every 3, 4, 5 days, the source Sagittarius A star flares up by up to a factor of 50 or so. And it turns out what happens here is that there is sort of a generation of very fast electrons, which then produce synchrotron emission during that time. And we can see with the interferometer down there on the left side that the material is polarized, there are these arrows, and it moves. It moves at a few times the event horizon size with essentially a third the speed of light. And so you can actually from this infer, number one, that the magnetic fields and on that scale, close to Sagittarius A star, are very, very strong. They have stronger energy density than due to the gas pressure, for instance. And then you can see that there is motion, which, if you interpret it as orbital motion, is equivalent to a mass of 4 million solar masses, which is exactly the mass you derive from the orbital motions of the stars, 1,000 or a few thousand times further out. So clearly there must be something compact. Now, another test we have been able to achieve at this point is the so-called Schwarzschild precession. So you will probably recall that in Newton, of course, if you have a single mass and a second object, test particles, orbiting around it, well, then if there's nothing else around, then the test object will stay on a say elliptical orbit for all times. Not so in general relativity. General relativity predicts precession of the orbits in two ways. One is in the plane of the orbit. This is the Schwarzschild precession. And the other prediction is if the black hole has spin, then there's a second precession around the axis of the spin. Now, the Schwarzschild precession we can see of this star on the right side, you see there is this ellipse again, and then you see basically that the Newton residuals would be zero at all times, but the general relativity residuals in red are a loopy thing having to do with the precession of the orbits, and the data are in very, very good agreement. Okay, now, of course, the next step would be indeed to measure the spin and the precession due to the spin. And then we can go to the, if you like, the holy grail of these tests, which is to test the no-hair theorem. Namely, the prediction by general relativity that you only have two quantities or three, which such an object can have: mass, that we can measure, and spin, and then charge, if you have charge. For these objects here, charge does not play a big role, because if you have a charge in interstellar space, you immediately get the current, which would decharge the object. So we at this point we need to measure the spin lens steering precession, and I'll come to that next. Now, the radio astronomers, their experiment is, if you have imagine a light source behind the black hole, which you look at in the radio wave. So that light source is this red little star. The photons go in all directions, but as they go into our direction, then if they're lucky and are far away from the black hole, then they come directly to our line of sight. That's n equals 0. Well, if they're a little closer to the black hole, well, then they actually get, shifted. I mean, the orbit gets shifted by some angle, which is quite substantial. And if the waves are even closer, well, then they orbit into the black hole and don't actually arrive at our place. So we would predict a central black region surrounded by a bright rim. And that is what the observation should show. And indeed, here is the measurement of our VLBI colleagues of the Sagittarius A star in 2017, and they published in 2022. And you see the central dark region there, and you see a ring. Now, there could be a number of interpretations, but we have, of course, due to the stellar motions, a prediction for the mass. So you put this prediction of the mass in there along with general relativity, then you would predict that the bright rim there produces a shadow of diameter 52 microarc seconds in the galactic center. And indeed, that's what our colleagues measure. So this is a very strong independent test of that this mass distribution in the galactic center indeed is a black hole. So we can say something about the motions of the gas, and about the central mass to be 4 million solar masses on the scale now of only a few times the event horizon size. Okay, so after this, of course, we will have one thing left to do. In that is indeed measure the spin, and that requires an object which is still closer. And sure enough, we have now found with the interferometry an object which is very faint, but you see it has an orbit. Um, I should go back here. Um, has an orbit which has a precession, a Schwarzschild precession of 2 degrees, not 10 arcminutes like the star S2, which I showed earlier. So here, really, you see the rotation in one period, and the prediction for if you have a spin is about a few arc minutes of additional precession around the spin axis, and that's what we're going to hunt down in the next 40 years, maybe. Uh, you see, you have to be patient. Took us 40 years and also our colleagues to infer the mass distribution in the galactic center, starting with Charles Towns in the 1970s. And then in this diagram, which is the enclosed mass on log units versus the diameter or distance from the central objects up on top in units of gravitational radii of a 4 million solar mass. And you see what you find is that initially the mass is a function of radius because, of course, you have an extended mass distribution in the stars. As you go within about a light year or so, then all of a sudden the stellar motions increase and you infer a constant mass of 4.3 million solar masses. We can measure this now, and also our colleagues in UCLA, with exquisite accuracy, about 0.1% accuracy, 4.299 million solar masses. And we can also measure the distance to the galactic center with similar accuracy. Now, that, as I told you, means we can measure the mass distribution enclosed within the orbits of these stars. But now the evidence from the new star and also the central shadow of the central region gives us the opportunity to measure the mass at even closer distance from the galactic center. And so at this point, one would have to say this object is a black hole, very likely. Now, of course, theorists would always say, no, you have to go all the way to the event horizon to really be sure. And I don't doubt that astronomers will try that step, probably be using gravitational waves as the test instrument. So far, however, the mass distribution indeed looks like a point mass, and indeed, if you think about the remnant mass, there's only a few thousand solar masses other than the central black hole. Okay, so that's the galactic center story at this point. Let me now go to more distant objects, back to the world of external galaxies and these quasars. And so our colleagues who have been doing that are able to measure, of course, there too, the masses in the central regions by looking at the motions of stars and gas, although by far further away than what we do in the galactic center. So you cannot prove that these are black holes, but you can ask the question, is there a central mass concentration? For instance, in our neighboring galaxy, M31. And indeed, the answer is that indeed you can find a compact mass in all of these galaxies, and essentially every massive galaxy. So if you plot this central mass, you infer on the vertical scale again versus the mass of the galaxy, then you get sort of a loose correlation. between the two. Where the Milky Way, which we've just looked at before, is sort of a dwarf in many ways. But here, of course, could do it there in much greater accuracy. So if you divide the central mass by the galaxy mass, you see that the ratio is approximately constant. And this is true for uh, galaxies at different distances from us. So if you think about this, how could that be? I mean, the galaxy, the outer galaxy, does not know that there is a black hole because unless it's a quasar, it would only be a gravitational effect, and the galaxy is much more massive than the central black hole. So this approximate correlation needs to be interpreted as a sign of evolution. The sign of evolution that the growth of galaxies over cosmic time and the growth of black holes over cosmic time are somehow correlated. And that is the story which I'm going to embarge on now. Uh, Now you can from these measurements infer that the fastest that the black holes would be able to grow without basically pushing the material back out through radiation pressure is about 400 million years. So every 400 million years, you can double the mass of the central black hole if you accrete a lot of material, but not faster. So the prediction is that these massive black holes are not formed very early on, but grow over time and then become, in the current universe, 13 gigayears after the Big Bang to the mass we see them. So now this general picture you can actually demonstrate very nicely in computer simulations. Here is one of dark matter growth in the early universe. You see, we're 1 billion years after the Big Bang here. These bluish filaments are dark matter concentrations. And then at their centers, overdensities grow from dark matter as well as normal matter, and star formation then leads to the formation of stars as well as falls into the centers uh, to enrich the mass of a possible black hole. This continues for a while until a number of things can happen. Supernovae explode as the most massive stars die out, or black holes send out flares and winds, so that the intergalactic medium here is full of all the dirt and junk which the activity of galaxy formation has created. But that is our current picture, how black holes and galaxies grew together statistically in an expanding universe. Of course, the expansion has been taken out here, so you see it looks like almost just a stationary effect. Okay, now we want to make these measurements of black holes, of course, very accurate and preferably on scales where we can be sure that they're really massive black holes, which I showed you we can do in the galactic center, but not in these distant galaxies. But indeed, we are beginning to be able to do that as well. Typically, these external galaxies with massive black holes have an accretion disk surrounding them. And because they produce a lot of radiation, an ionized gas zone we call the broadline region, that's these blue clouds. And that around that is a region of more normal gas. So these blue clouds empirically are virialized to the mass of the central object. And so by measuring the time variability of the central black hole candidate and then measure the velocity width of the broadline region, that allows you to do what we call reverberation mapping, namely to infer the mass on scales of, say, 10,000 times the event horizon. Now, with our interferometry, we can actually do this directly now by measuring the motions of these broadline region clouds, and thereby get information on the mass distribution. So here you see, in fact, this quasar, which I showed you before, 3C273. Then you see on the left side and the top, the profile of the Paschen alpha recombination line of hydrogen. And then the interferometer measures for each point in the spectrum a phase. And that phase is a signature of the position. And you see there is sort of an S-shaped type variation, very small, only of a few microarc seconds. Now that you interpret then, like on the right side, as an accretion disk, which is rotating. And that from that you can get the mass of the central object, and of course also the size of the broadline region. So this is our new technique to infer distant galaxy masses uh, indirectly through the reverberation and directly through our interferometric technique. This, in fact, is a distant galaxy where we've done it with interferometry, which is really challenging work. And if you plot now the black hole mass on the vertical scale versus the inferred stellar mass, then the curve I showed you before is that dark region on the right, a dark stripe on the gray stripe on the right side. So that's what we see in the local universe. Now at high redshift, you see a story becomes more interesting or more difficult or more spectacular. The masses of the central objects seem to be larger relative to the stellar mass than in the local universe. So that was totally unexpected when this information started to come in about 2 years ago. And as I said, it's placed on two measurement techniques. One is the reverberation with the James Webb Telescope, and then also our interferometry. So we think that black holes formed very, very early and grew approximately with the galaxy, but initially very fast, and later on not so fast. Now this finding is being discussed right now amongst all astronomers. How could such early massive black holes have been created? When I told you that it takes, in the normal interpretation, 400 million years before a black hole can double its mass. Here we're talking about black holes which are only, say, a gigayear after the Big Bang. There's not enough time to grow through normal accretion to that mass. So there's a lot of discussion. One is that this Eddington limit, which I mentioned to you, with the 400 year doubling time, is not right. If you bring material, say, in a disk in that way, and the radiation goes out that way, then the radiation pressure will not be effective in the incoming. So that allows you to go faster inwards. Another one is to form star clusters early on, much earlier than we thought, and then these star clusters collapse to a first black hole. And finally, there is an old friend which had been speculated about earlier, namely primordial black holes. Could it be that already during directly after the Big Bang, black holes formed and then basically grew through accretion and merging and so forth? Well, we don't know yet, but this will keep astronomers and gravitational wave community busy for the next 30 years, I'm sure, until we understand this. Well, thank you.
Thank you very much for this wonderful lecture and finishing movie. So we see that black hole physics is also applied physics.
Black hole is very useful thing.
Yeah.
So then we could move to questions and answers session if you allow. We already have a first question from Mykola Bondarenko.
Good evening. Thank you very much, Professor Genzel, for the fascinating talk on the fascinating subject. I was wondering about when you showed this explanation for the dark spot on the orange donut, that possibly there is a light source behind it, and this is why the light cannot pass directly through the center of this object. But I was wondering why the source must be behind the hole. If it is somewhere sideways or in front of the hole, there should be no dark spot.
You are absolutely right. In fact, my analogy I drew to explain what was approximately happening with the light bending of a source behind is just sort of a crutch to explain what happens. Indeed, the correct picture is the central region, as I talked about later, is surrounded by hot material, hot plasma. That hot plasma emits radiation, and so you don't have a light source behind, but basically all around the black hole. And so still the effect of the central donut, so to speak, is an effect you can observe. Now you see, of course, that the the sharpness of the drop currently available through the measurements available is not yet at the level where you would, be able to measure very detailed numbers like spin and so forth. So that is something which still counts. But indeed, I gave you a simple explanation where the more correct, more complicated situation is a distributed gas, hot gas region that emits around the black hole.
Thank you. If time allows, I have another question. Well, I was curious about these trajectories of stars around the black hole. They look like elliptic, basically, but are they Keplerian? You even showed these deviations due to general relativity.
Yeah, so let me go back to this picture. So indeed, I mean, what you see here are, a few of the objects which we are tracking with our measurements. And indeed, what you find is that as you go to the center of this region, close to the black hole, the orbital distributions of the star become ever more elliptical, yeah, almost parabolic. Yeah, I mean this star, which let me go to that one.
And then
That one, the red one there, that has an ellipticity of 0.998. Now, why would that be? Well, the answer, I think, we believe, is the region, the mechanism for these stars to come into the central region is a scattering mechanism. A scattering by masses from further out, such that the stars come in on highly elliptical orbits, so that within the lifetime of a star, they actually make it to the near black hole environment. If you wait until basically Maxwellian redistribution through collisions in the star cluster moves stars to the central region, there are only black holes left, stellar black holes. So the more massive bright stars which we are using here, so to speak, have to get an extra kick in radial direction, and that's why the angular momentum is so substantial.
And I was curious, are there traces possibly of dark matter influencing those stars? Or
Yeah, I mean, you see in this picture right in front of you, the measurement situation as we have. So let's put all the information on which we have. So we have these mass measurements, and you are free to postulate dark matter distributions. In fact, that has been done. Now, the central concentration of dark matter depends, of course, on the mass of the dark matter particle. Okay, that's the Oppenheimer-Volkoff limit. And in fact, if you have a 50 kilo electron volt fermion ball, for instance, take neutrinos or something like this, then its radius would be as large as the innermost stars. So that can be excluded right there. If you have a more compact, because larger fermion ball, then at least for the stars, you cannot exclude it. But these innermost motions of the gas, and as well the radio size of the torus, excludes almost everything other than maybe boson stars. Now these are totally hypothetical objects, of course, and then we can make another statement. We can make a statement on the basis of Occam's razor, because if you go to a galaxy with a still bigger black hole mass, well then if it's not a black hole, but there are bosons in there, then the boson mass has to be still larger, and that would not be possible. So I would say dark matter solutions are basically out, but definitely the last few years we have used our measurements to make strong constraints.
Thank you. And the last question, please, Phil, are those anisotropies of the central object in the galaxy center correlated somehow with the greater structure like a galactic bar or something like that?
No, they are not. They are beautifully isotropic, but highly elliptical. So if you make an orbital distribution map, then you will find isotropic, but the closer you come to the black hole, the more elliptical, okay? And that we interpret through the mechanism which I explained to you, which has been first proposed in the 1980s by Mr. Hills to basically bring stars from a large distance to the center very effectively.
Yeah, thank you very much.
Thank you. I saw a raised hand by Professor Alexander Karduk. Do you have still a question to the speaker? Or?
No, it was already answered. It was
okay. Thank you. So the next, Konstantin Lukin, please.
Okay, thank you very much. Thank you, Professor Genzel, for very informative presentation. I was involved a little bit in this area measurement of the event horizon, and
okay,
but I think it's just involved, but not really work on.
Well, congratulations, Owen.
So I know. So I have two slightly different questions related to first the measurements. My question, the picture which you show us now for Sagittarius A star measurements, and you achieved the super resolution because first, which frequency band this image was?
1.3 centimeter, millimeter.
Millimeter.
Yeah, so
okay.
This is the shortest wavelength radio astronomers can.
Yeah. But it is known that for these type of frequencies, the resolution, angular resolution for any network of telescopes on the Earth is not sufficient to resolve this image in the Sagittarius A1.
You are absolutely right. Yeah.
My question: have you used this Or do you know that people use this super resolution technique, like Bayesian estimation?
Yeah, no, you're putting your finger on a number of issues. Let me briefly explain. So the way radio interferometry produces images, as you well know, is you measure at a given time the fringe contrast and phase between two telescopes, and then for all combinations.
Yeah, yeah.
And then you measure this again and measure it again over as long a time as you can. And then the Fourier inversion of the complex fringe visibilities gives you an image. That has difficulties in the galactic center, unfortunately, because the galactic center source is highly variable. In fact,
You
it's
know,
variable.
okay. Keep going. I'm just
Yeah, I mean the basic situation is that the time scale for variability at the photon orbit in the galactic center is only 20 seconds. Okay, and so if you measure over 5-6 hours, then the probability is very strong that the image and therefore the fringes visibilities have changed. So the image reconstruction is rather tricky. And as you say, different technologies have been used, broadly giving the same result. But it has prevented, so to speak, a pushing to the limits of the interferometry at the angular resolution of a globe-wide interferometer. What is the solution? The solution is, one, you could go to shorter wavelength. But that is not possible because as you go from 1 millimeter down to, say, 800 micrometers, the atmosphere really is not transparent anymore. So you cannot get
right.
good measurements. The other alternative is space. And
Yeah.
the interferometry community has been trying, both in the US as well as in Europe, to propose such a space interferometer. But unfortunately, the space agencies tell the community that this experiment is too expensive. So we're a little stuck there.
Yeah, we slowly move to my second question. Exactly, I wanted to ask about the status of the Event Horizon Imaging Experiment. They suggested by Manuel Martinera, and Falke, and it was
Yeah.
approved. Event Horizon Imaging. That two
Uh,
satellites launch on the low orbit for 100 kilometers,
mhm.
and with slightly different altitudes. And when they're moving with different velocity, the baseline between these two receivers installed in these satellites gradually increase. And in this way, they created a virtual dish which well exceed the dimension of any interferometer based on the surfaces, as it was in the Event Horizon Telescope experiment. And then resolution will be sufficient to get the image Sagittario A star, supermassive black hole. But
Yeah, you're
and it was
absolutely.
what I know, financially it was supported, approved by ESA. I wasn't at that seminar when it was declared. It's $500,000, but financially gradually it should be, including.
No, I don't think so. I mean, it's very clear, and I fully support this, that the EHT community pushes for this experiment which you're describing. Absolutely the right way of going forward. It's just the reality is that NASA is not in good shape, and ESA just does not have the resources at this point to follow up on this. However, make sure ESA is supporting what I would regard as eventually the ultimate experiment, and that's LISA, the gravitational wave instrument in space. Because with that, you can easily go to very large distances and sub horizon scales and make measurements. So I would say that is difficult enough, but I very much hope that this gets realized. The radio interferometry, well, I'm sure that Heino and others will try again to convince ESA to go for it, but it's a bit of a question how much money is available.
Yes, thank you for the answer. I just in May this year, I visited conference in Estate, but for another topics area. But then in coffee break, I asked some engineers from Estate, do you really believe in this image obtained from this M87 super heavy black hole? They just gently smiled. So, which means,
Yeah, well,
so
look,
because
you're absolutely right. I trust my colleagues, since I've worked myself on the interferometry, space interferometry, and VLBI, I know what they're doing. I know how hard they've been working. But indeed, it's at the very edge. That image you see there, that image is really at the very edge. Now they've tried different ways of using the data, and of course, the next thing they will try is to use the variability of the source by basically making a movie. And then basically over time have a number of incomplete pictures, but then you basically separate out the variable part and the constant part, and the constant part, then you can hope that has better resolution than a single epoch measurement.
yeah, the direct resolution will be might be convincing and assure all people to try to believe in this measurement result. I'm not trying to tell that they're cheating people. No, it's impossible. For scientists, it's impossible. Then the methods were used. They used the Bayesian estimation and the a priori distribution function they took from the theory, which supposed the black hole in the center of this image. And then it's like the suspicion that maybe they gave them so nice result. I don't know. This I did not investigate this area. Just decided
Yeah,
to ask
well, I
you.
mean, you're putting your finger on soft things. Uh, let's say the following. This is a very difficult experiment, especially in the galactic center because of the variability. But they have had a lot of people on the analysis, and there are different techniques of extracting the images, and they sort of come out with the same result. In the case of M87, maybe you've seen that a Japanese group recently has published a result which is not consistent with the EHD. So I would say one has to accept this is at the very limit and needs to be solidified by more measurements. But measuring at 1.3 millimeter across the globe is also difficult because of the weather. Yeah, I mean, so it takes a long time. You see, this image here is the practically the only image we have available in the literature, yet it is the data were taken in 2017. So that tells you something already about the probability of getting new information over that time scale.
Yeah, I think my opinion that if this experiment, event horizon imaging, will be implemented, it will be fantastic, give fantastic results. Fantastic and very, but unfortunately, Martin Neira is on pension now. He was very much enthusiastic, including with Hauge. Sorry, I took too much time, but I think it's. Thank you for your explanation. Thank you. Thank you very much for your presentation.
Thank you, Professor Lukin. The next question we have from chat from Dr. Maximenko. Will you spell your question or I will read it? Okay. Thank you very much for the interesting presentation. I have a few questions. The first question is there an explanation for why the primordial black holes that formed immediately after the Big Bang have not yet evaporated as a result of Hawking radiation?
No. So the hope is that holes, in fact, there are theoretical papers on this just in the last few years, because the interest in the particle physics community has been great in exploring this, primordial black holes as an alternative to dark matter. So it's clear that there will be a spectrum of such black holes formed, and you are quite right that the lower mass objects are more common, but they are also less stable. So they will evaporate by Hawking radiation. But the hope then is that there is a more massive tail, and that would then survive the first period and then start growing or accreting material and et cetera. But this is all speculation at this point. We cannot say whether this is a true pathway, but we should definitely look. You see, how could we test it? If the primordial black holes have a component which is massive enough, let's say half a solar mass, then they would not be able to be produced through the standard mechanism of the explosion of massive stars. Okay, but they might then have a primordial origin. But you would still have them somewhere, like for instance in the halo of the galaxy, in which case weak lensing might be the technique to hunt for them. And the Ogle experiment, which now has the longest track record of 2 years, 20 years, basically has not found any longer period weak lensing case, which could be such a half solar mass black hole. So the observational evidence is not there, but I'm sure it'll be tried again. It's a highly popular proposal right now because the desperation on the lack of evidence for the supersymmetric particle or axions or something like this at this point. Of course, physicists will look for other explanations.
Thank you. And the second question from the same participant, your opinion on that. Why do you think the Spectre R telescope, which had such a high angular resolution in the radio range, was still unable to detect a black hole in our galaxy?
Well, it's just the resolution, okay? I mean, the resolution, at best, if you could really get to the diffraction limit through the Fourier inversion, at best is about 20 microarcseconds. And in the galactic center, the event horizon, the expected size of the torus is about that. And so you're in this murky situation where your resolution and the predicted size from general relativity are approximately the same, and then if the signal noise ratio is not sufficiently large to filter out, well, then you get a sort of an unclear result. But that's a negative way of looking at it. My way of looking at this was we have an absolutely super accurate measurement of the mass on top, but at larger radii, and then we have a totally independent test of the size of the event horizon, which agree within 20,
Right.
30%.
Thank you. We have the next participant, Gleb Skorobogachka. Short question, if possible.
Okay. First of all, thank you for a very interesting talk. My question is correlated with the question by previous participant. How do you think can these new findings, especially mass distributions, the mass distribution diagram, which points out on the fast formation of massive black holes, can this data point out that the speed of Hawking evaporation of primordial black holes is much lower than theory predicts? So can one expect any sufficient differences between theory and observation in this respect? Thank you.
I have not seen an analysis of that type. Okay, I myself, of course, have not worked on it, but from what I've read, is the expectation is this. For instance, in the paper by Bernard Carr in 24, expectation is a very flat distribution of mass of primordial black holes, and then the most massive ones, of course, you cannot hunt for, because they would look the same as black holes, which are formed in different ways. So it's only the low mass end, and the most common predicted primordial black hole mass is 10 to minus 4, 10 to minus 5 solar masses. That's impossible to see. So you're left off with this sort of part in between, and if that is present, then you can hunt for it through, as I said, weak lensing, etc. I'm sure we will also go for this now with the interferometry, because there is a lot of emphasis in future years on time variable sources, time domain astronomy, and so then we can hope, for instance, to hunt down intermediate mass black holes and see where they are, and could they have been, so to speak, of an older or an origin, or were they formed in a similar way in the cores?
I mean, then the possible mechanism of formation of massive black holes can be due to merging of primordial black holes. Can it be? And then in that case, one need primordial black holes to be stable, not to be destroyed by Hawking radiation. That's my question.
Well, that's right. If they are low enough mass. But I mean, let's be sure the black hole masses of 10 to the 9 solar masses, etc., that growth is totally dominated by gas accretion, baryonic gas accretion, in particular during mergers. If two galaxies merge, that's the most impressive way to remove angular momentum in the galaxies and channel material into the centers.
Okay, thank you.
Thank you. We have one more question from Andrei Terehov. Would you ask?
Yes. Thank you. Firstly, thank you so much for very interesting lecture for me. And I have very simplest questions for you. What do you think about existing gravitons?
What?
What do you think about existing such particles as gravitons?
I can't really say. I mean, this is we would have to have from the particle physics community some very solid predictions, which we can test on the large scales. Now, it's very clear right now there is, I would say, almost a hype in the theoretical particle physics community to come up with all kinds of explanations of that type. But Most of these explanations, I don't know whether we have a chance to test them with the methods we have available. But let's give it 20 years, okay? Let's give it 20 years when the gravitational wave in the interferometry is running, because then I think we can more easily go down to the very near event horizon scale.
Okay, thank you so much.
And we have perhaps a very nice concluding question from chat. Professor Genzel, how do you view the journey that led you to the Nobel Prize? And what advice would you give to young researchers?
Yeah, well, okay, I was lucky, and I was also blessed with a fantastic set of mentors, in particular my own father early on, and then Charles Towns. Charlie really was the person who put me on the Galactic Center trail, so to speak, and he always had dreamed to use interferometry. He couldn't manage that anymore, but the fact that I sort of had the right idea how to enter the forest of research was a very important one. Next, I've had the extremely good luck to be in an organization, the Max Planck Society, which allows directors to have fairly large groups over a long time and take risks. See, most researchers live on grants, which are 2 years, 3 years. This work took 40 years, and so you have to be able to take risks. Whether you have new detectors, if you want to use the laser guide stars, all of this, what I talked a little bit about on the side, is something which took a lot of work by many young people. So excitement, dedication, having the right mentors, and stay with it.
Thank you very much for such an answer, and thanks, Dmitros Efimovic, for the nice question. So with this, I would like to thank you for such a pleasant conversation, questions and answer session, and for beautiful presentation. Thank you
Thank
for
you
your
very much.
support.
Thank you for having me. It was a great.
Dankeschön.
Okay, goodbye.
Thank you. Goodbye. All the best.
See
All
you.
the best to you.
Thanks.
You are the ones who.
Thank
I
you.
wish.
Stay strong.